Hey everybody, Trey here. Welcome back to another video. Back with another case study today, and we're going to take a look at one of the more notable tornado events of the last couple decades. And this was actually the first tornado to be rated EF5 under the new enhanced Fujita scale back in 2007. And that is, of course, the Greensburg, Kansas EF5 tornado of May 4th, 2007. An absolute beast of a tornado, as you can see from the image here. Was about 2 miles wide at times, and actually took a direct hit on the town of Greensburg, destroying about 95% of the town. So, very upper echelon event for sure. As always, we're going to take a deep dive into the meteorology behind the event before discussing some of the characteristics and behaviors of the parent supercell and the tornado itself. And I think any discussion of the Greensburg event would be incomplete without mentioning the tornadoes that occurred after the Greensburg tornado. This supercell was an upper echelon supercell, produced 22 tornadoes over a 6-hour period or so. The most notable of which, of course, being the Greensburg tornado and the ones that came after it near Trousdale, Hopewell, and Maxville. A lot of the characteristics of the Greensburg tornado can be applied to these subsequent tornadoes, but we're going to talk about their evolution as well in this video. So, as always, I am going to be referencing quite a few journal articles and papers from this event, specifically Lemon and Umscheid 2008. That was a very in-depth paper about this particular event, as well as a few others. And of course, I'll put the links to all these papers in the description box below so you can do some research on your own. So let's go ahead and get started here. Just to give some context, May 4th was actually not expected to be quite as potent as the following day. The following day was a pretty well forecast severe weather outbreak. Day 2, moderate risk here across much of the plains, that was upgraded to a high risk by the morning of May 5th. So May 4th was kind of expected to be the day before the day. There was still expected to be quite a bit of potent severe weather on that day. Moderate risk out for parts of eastern Colorado into southwest Nebraska, western Kansas, into northwest Oklahoma, with a 15 hatched area for tornadoes coincident with that moderate risk, as well as a damaging wind and significant hatched hail area there in the central plains. So there was expected to be quite a bit of potent severe weather on May 4th, but there were some caveats, and we're going to talk about those caveats in this particular video. So let's go ahead and dive in here. We'll start at our 500 millibar map as we always do, and if you were to look in the dictionary under classic Central to Southern Plains tornado outbreak, you'd probably see a pattern that looks something like this. Big old trough here centered across the western half of the country, big old ridge here centered across the eastern half of the country. But one thing we can notice here is that this trough is kind of lagging back here behind a little bit. If we were to draw kind of the axis of this trough, it'd be somewhere kind of right in here from the Pacific Northwest down through the desert Southwest. The main belt of flow associated with this trough kind of hanging back here out across the west coast. So this trough was still kind of in the maturing phase on the 4th, and it wasn't expected to really eject into the plains until the overnight into the morning hours on the 5th. You can see here as we go on with time, the trough doesn't really move a whole lot, starts to dig a little bit, take on a little bit more of a negative tilt. This kind of stronger flow starts to round the base of this trough and kind of eject into the plains into the overnight hours. And you can see by the morning on the 5th that we really started to get that kind of exit region to encroach into the central and southern plains states there. But for most of the day, this trough was kind of lagging a little bit behind, and that was going to perhaps create a little bit of an issue for this particular event. We'll take a look at that in a second. But still, nonetheless, very strong trough, little bit of southwesterly flow here encroaching into the central and southern plains here. So all we needed really was a little bit of a shortwave trough to kind of move into the region to help us out a little bit. Let's go up to 300 millibars here and take a look at our kind of diffluence and divergence fields here. So we've talked about divergence and diffluence before. Diffluence is kind of the spreading apart of those wind vectors with height, that directional divergence of those wind vectors with height, and that creates kind of a void. And the atmosphere doesn't like to have that void in place. So what happens is the atmosphere tries to bring up air from below, and that allows for the large-scale rising motion to initiate storms in a given environment. You can see here as we go to 300 millibars, as we go through the day, you can see as we go kind of toward midday or so, the main kind of diffluence or directional divergence associated with this trough is kind of hanging back in here. You can see across Utah, winds out of kind of the southwest there, over Arizona, more out of the due west. So the main defluence aloft kind of associated with this particular trough was kind of lagging a little bit farther back here out across the desert southwest. And so, normally we'd like to see that kind of, somewhere out in here, out across our kind of target area. But that wasn't really the case until we got into the kind of late night, into the morning hours on the 5th. You can see here, very strong defluence moving in by 12Z on the 5th out across the Central Plains. And that's why the 5th was expected to be a little bit more active, a little bit less conditional of a threat, especially down the dry line here for the Central Plains on the 5th. So, main message here is that the main trough was kind of lagging a little bit farther back. The main forcing associated with the trough was lagging a little bit farther back. And all we needed was a little bit of a shortwave, a little piece of energy with a little kind of kink within the main flow, the main wave, to kind of move through and help us initiate kind of a localized area of enhanced ingredients for severe weather and storm initiation. And as we start at 12Z here at 700 millibars, you can see lots of little kinks here within the flow, within this kind of broader, kind of large-scale wave here at 700 millibars. And if we go through with time here a little bit, I want you to keep your eye here right on kind of the El Paso to New Mexico vicinity. You can see this kink right in here, kind of a well-defined kink, kind of centered western New Mexico down toward the far west Texas area. This was a shortwave that was expected to move through, kind of timed well with kind of the late afternoon sort of initiation period with this particular event. As we go through with time, it's a little bit tough to track here, but you can see by about 22Z, our wave is kind of somewhere right in here. It's moved off toward the east a little bit of a kink there, and that is where we were expecting storm initiation by late afternoon, kind of right in the Texas Panhandle to Oklahoma vicinity, despite some caveats that we'll, again, talk about here in a second. But we had a little bit of a shortwave moving through. Easier to see on water vapor satellite imagery. Unfortunately, I couldn't find any of that archived data as far as water vapor imagery goes. We do have infrared imagery, and so we'll take a look at that. And this is starting at 13Z, so about 8 a.m. on May 4th. We go through with time here. Keep your eye on the Texas Panhandle to New Mexico region. You'll see as we go on with time, we get this kind of batch of cirrus to develop by mid-afternoon there across the kind of Texas Panhandle to New Mexico vicinity. You see that cirrus right in there. That likely is kind of the leading edge of that forcing associated with the shortwave. And we've talked about cirrus before, particularly with the May 3rd, 1999 Oklahoma tornado outbreak, that oftentimes cirrus is going to be a hindrance for storm initiation. Oftentimes that will kind of limit surface heating and decrease surface temperatures so that you have a little bit a tougher time to initiate storms when you have a batch of cirrus. On the May 3rd, 1999 event, we had kind of a break in the cirrus that allowed those discrete storms to fire in southwest Oklahoma. Here, kind of the same thing, patchy cirrus over the region. We'll go to our visible satellite here. Starting off in the morning hours, we'll go on with time. You can see mostly clear skies here across southwest Kansas into Oklahoma and the Texas Panhandle. So lots of surface heating going on, and you can see as we go on with time, you get those cirrus to start to move in. By about 21Z, we start to see a little bit of cumulus development down here in the southeast Texas Panhandle, right on the leading edge of that kind of cirrus plume. But enough breaks in the cirrus to not really hinder surface heating, and we did get storm initiation by about 22Z, right there on the Texas-Oklahoma border there in the northeastern Panhandle. So there was some cirrus, likely the leading edge of that little wave there, and that was kind of an impetus for storm initiation down along the dry line there in the afternoon on the 4th, going into the evening hours on the 4th. Now, as we talked about, our main forcing with the upper trough kind of lagging behind a little, and that had some implications on the low-level cyclogenesis. We've talked about cyclogenesis before. It's what happens when you have southwesterly flow traversing the Rockies, and you get sort of that air to sink down the Rockies, and you get surface low development on the east or lee side of the Rockies. We do have, as we went through the day on the 4th, we did have enough kind of southwesterly flow here, kind of muted southwesterly flow. Again, the main kind of enhanced belt of winds rounding the base of this trough, still on the backside more so of this trough. So kind of a muted low-level response here, and you can see that in the 850 millibar fields. As we know, 850 millibar is where we look for our low-level jet. As we start the day on the 12th, you can see just kind of broad cyclonic flow here out across the kind of Four Corners region into the central to southern high plains there. So just kind of broad cyclonic flow there. And that was going to kind of remain that way throughout much of the day. You can see as we go through the day, our low-level jet kind of decreases quite a bit there. Central to southern Kansas, only about 10 knots here up in northeast Kansas to about 25 knots in central to southern Kansas. So not a very strong low-level jet in place here. And that was because of that kind of muted mass response and low-level response associated with kind of muted cyclogenesis and that kind of a factor or a consequence of the main forcing lagging behind a little bit with the mid to upper level trough here. We do get some consolidation and intensification of that low level cyclone here as we go into the late afternoon and evening hours. You can see the low level jet does ramp up with time as we get this cyclone to tighten up a little bit here across kind of the Colorado, Wyoming, Utah vicinity. And this is going to be a huge critical key in the evolution of this event. You can see the low-level jet by 3Z has ramped up to 45 knots or so out across Oklahoma into southern Kansas. And we'll come back to this a little bit later here after we take a look at our surface map. So let's take a look at our surface data here. And you can see a lot of similar things here. So first of all, let's take a look at our moisture. See 60s dew points up into southern Kansas, down in through Oklahoma, a little bit richer moisture as you go down with southern extent into Oklahoma. 60s, upper 60s to 70s dew points there in southeast Oklahoma. But again, muted kind of low-level response, muted low-level jet throughout the day. We were going to have to wait until we got a little bit better response here going into the late evening, into the overnight hours for this surface low to really tighten up, really consolidate, and really start pushing that moisture northward. And that's what we got come late in the day. As we start the day, 12Z, you can see that we have just kind of broad cyclonic flow once again here at the surface. Southeast Colorado wind barbs here, kind of out of the due west or so. Oklahoma Panhandle more out of the southwest Kansas, kind of southeasterly winds, northerly winds here across eastern Colorado. So just kind of broad cyclonic flow here. It's sort of a weak surface low centered somewhere kind of at the Kansas-Colorado border there in southeast Colorado, southwest Kansas. And I want you to keep your eye on this particular station right in here. I believe that is Springfield, Colorado, if I'm not mistaken. So we start out here. Notice our pressure at 999.8. Again, we're going through all this kind of how to read surface plots and stuff in our weather map analysis series. So if you're unfamiliar with how to read these surface station plots, go ahead and check out part 2 of that video series. I'll put a link to that in the description as well. But so our pressure here, 999.8, and notice that we actually get some pressure rises here throughout the early portion of the day. We rise to about 1002.5 millibars there at that particular station. And just going back to 500 millibars real quick, we actually started the day with a little bit of ridging aloft over this region. You can see the little bit of a ridge in place out across kind of western Oklahoma, eastern Texas Panhandle, moving southward. So a little bit of ridging there. Over top of the area to start the day. Of course, we would get that trough to move in a little bit and kind of negate that ridging aloft. But that ridging aloft was going to perhaps suppress things for a little bit as we went through the day. And you can see those pressure rises associated with that kind of ridging aloft there at the surface. So we go on through the day, and you can see as we go into midday into the afternoon, we start to see that pressure really fall there at that particular station by 22Z down to 996.6 millibars, and you can see a little bit tighter of a circulation there across southeast Colorado. So we had really kind of tightened this surface low a little bit as that southwesterly flow was trying to make its way over the Rockies, trying to increase that cyclogenesis response there across southeast Colorado, and that's exactly what we got. You can see the winds here out across the plains, 15 to 20 knots here. Those had kind of strengthened with time. Moisture still slow to make it up here into southern Kansas, into eastern Kansas, not a big deal there. We see dew points in the upper 60s to low 70s even, but our 60 dew point line kind of somewhere in there. Dry line developing out here across the southern plains, with kind of a pretty strong bulge there in the dry line. This is again at 22Z, so about 5 p.m. Central Daylight Time. Broad kind of surface low, consolidating a little bit there in southeast Colorado. So our dry line, somewhere kind of in this vicinity right here, you can see the difference between the dew point values on either side of that line. So perhaps a very strong dry line bulge there across southwest Kansas, a little bit of one maybe in here across the Texas Panhandle. You can actually see some localized convergence here develop at about 22Z, right in the northeastern Panhandle near Pampa. the wind barb at that particular station out of the southwest, more southerly or south-southeasterly winds here out across the eastern panhandle, leading to a little bit of convergence on the leading edge of that shortwave, and we were able to get storm initiation right in that vicinity where that convergence started to manifest itself by 22Z. Now, as we continue on with time here at the surface, you can see that pressure continue to drop at that particular station, and by about 2Z, you can see that the dry line, because this low was kind of strengthening here in southeast Colorado, that moisture, the low-level moisture, was really trying to make its way west. The dry line was kind of migrating back toward the west a little bit. You can see Dodge City here now with a 75/63 station reading there, so 63 dew point, whereas a couple hours earlier, the 60s dew points were much farther off toward the east. So that dry line was making its way back toward the west a little bit, and that was how we got that moisture up into southwest Kansas to allow for severe storms to continue into the evening and overnight hours into Kansas. And you can see by 4Z, mid to upper 60s dew points, mid to upper 60s and even 70s dew points up in here across central to southwest Kansas there. So let's take a look at some sounding data now. Usually I like to look and go back and kind of look at a sequence of the RAP model soundings. In this case, it would be the RUC model soundings in proximity to the particular event. Unfortunately, I wasn't able to find those particular soundings, but we have some observed data to look at here. So we have our Dodge City soundings, 12Z, 18Z, and 0Z, and the same for Lamont, Oklahoma, which is in far northern Oklahoma, just southeast of kind of the Greensburg area. So we'll start off with Dodge City here. And this is kind of the main issue with these day before the day events. This pretty stout cap here, above about 850 millibars. Very steep layer, very deep layer of steep lapse rates, warmer air aloft, which is of course our elevated mixed layer. We talk about this every video. That elevated mixed layer is that layer of warm, dry air that originates from the surface in the desert southwest or western Mexico and makes its way into our particular region of interest in these severe weather events as that kind of westerly or southwesterly flow in the mid-levels transports it off toward the east atop a moist layer near the surface. So the elevated mixed layer was extremely strong. That's often the caveat with these kind of day before the day events. You often have these strong elevated mixed layers in place, but because the trough is lagging a little bit farther behind, and oftentimes shortwave development moving through the larger scale wave is a little bit questionable, oftentimes it's tough to get this elevated mixed layer to erode. And we've seen that a lot in the past several years, especially with the drought being so prevalent in the southwest. The elevated mixed layer tends to be stronger, and oftentimes these day before the day events end up being cap busts because the elevated mixed layer is unable to be eroded because you don't have that forcing moving in, the main forcing moving in to lift this elevated mixed layer and cool it and help erode it fully for storm initiation. So this was a little bit of a caveat, especially farther south along the dry line into the eastern Texas panhandle into western and northwestern Oklahoma. Wasn't 100% sure that this would erode fully down the dry line. So a lot more conditional than farther north into, say, Colorado, where you had upslope flow, a little bit closer proximity to the actual wave. That was going to help things get going there across kind of eastern Colorado, northwest Kansas vicinity. We start off the day there, as we said, with a very strong looking elevated mixed layer. Pretty shallow moisture here at Dodge City, only a 57 dew point. Doesn't really extend that far into the atmosphere, just a little tiny layer there off the surface, so not very deep moisture at all. And you'll notice as we go through the day what happens with our hodograph. 12Z do have a little bit of kind of warm advection, ongoing veering of those winds in the low levels, but by 18Z we had really decreased that low level shear. You can see very weak low level shear by that point, and we saw that again, that muted sort of cyclogenesis, low level response as that upper to mid to upper level wave was kind of trailing behind. We did have that cap remain in place through much of the day. Moist layer deepening a little bit with time. You can see moisture by 18Z at Dodge City up to 61 degrees there. And then by 0Z, Dodge City was behind the dry line. You can see a well-mixed boundary layer kind of behind the dry line, layer of very well-mixed air here, inverted V profiles there behind the dry line. But notice what happens to our hodograph there. Very strong-looking hodograph here by 0Z at Dodge City. You can see some veering of those kind of winds in the lowest few kilometers there. And so overall shear was increasing, especially low-level shear, and you can see that a little bit better at Lamont, Oklahoma. Once again, kind of a shallow moist layer beneath that elevated mixed layer aloft. A little bit less pronounced here with eastern extent. You can see not quite as strong of an elevated mixed layer there into northern Oklahoma. But notice what happens with the moisture. Moist layer deepens considerably by 0Z here. You can see that moist layer extends all the way up now to just above 850 millibars there. So much deeper moisture moving in, thanks to that low-level jet slowly increasing with time and really ramping up as we went towards sunset into the early evening hours. And you can see our hodograph here by 0Z at Lamont, much more favorable for severe weather and tornadoes. Lots of veering of those low-level winds, deep layer shear increasing to about 40 knots or so. So this was definitely a supercell profile with the threat for all hazards. You can see large CAPE there, mixed layer CAPE above 4,000 joules per kilogram. Low level CAPE, even though we still had a little bit of this inversion to stick around, 0 to 3 kilometer CAPE at just below about 100 joules per kilogram. So very strong low level instability there. But we still had this inversion to deal with, and that is often something to consider with these nighttime events. We'll go on to our 3Z ruck sounding in proximity to the Greensburg case. This is from the U.S. Tornadoes Case Archive here, and you can see what happens to that hodograph by tornado time here across southwest Kansas. Very impressive looking hodograph. Very strong veering of those winds in the lowest levels of the atmosphere. 0 to 1 kilometer storm relative helicity, over 200 meters squared per second squared. So very strong hodograph, strong looking hodograph there for significant tornadoes after dark. And you can see what happens to that low level jet. 1 kilometer wind had really increased by this time. And you can see from this graphic from UMSHI 2010 what happened to the hodograph at Dodge City throughout the day. Red is our 18Z hodograph at Dodge City. Blue is the 0Z. And the 240Z is this black line here. This was a vertical wind profile from the Dodge City WSR 88D radar. And you can see exactly what happens to our hodograph with time. You can see it at 18Z, very weak shear, very weak low-level shear. Starts to increase that low-level shear and deep layer shear by 0Z, but by 240Z, as the tornadoes were ongoing, just an absolutely massive looking hodograph there. Very strong shear in the low levels, some very strong veering of those winds in the low levels with height. The ramp up in the low-level jet in the early evening hours was a critical piece to this particular event. Again, the timing was very nice as you had that shortwave move through right in the late afternoon to early evening, and you had just enough southwesterly flow to start to increase that kind of cyclogenesis effect there in southeast Colorado. So a little bit of a ramp up in the surface features. The low-level jet, as a result, ramped up as well. The low-level jet does tend to ramp up on a diurnal cycle, so it does tend to ramp up at night. But that kind of increased cyclogenesis there in southeast Colorado, southwest Kansas was definitely aided that increase in the low-level jet after dark. And this is a fairly common situation that we will see in the plains. And a particular analog to this event that came to mind was the May 24th, 2015 tornado event in southwest Kansas. This was a kind of a ho-hum severe weather day for most of the day. Just kind of a slight risk there across southeast Colorado into the panhandles, southwest Oklahoma. Just a 2% tornado threat with damaging wind and large hail threat there as well. Storms did kind of congeal into a line there across southeast Colorado, but a lone supercell fired up out across southwest Kansas near Liberal in the early evening hours as the low-level jet was ramping up, and you can see what happened here. Became a cyclic tornado producer as it moved toward and produced a large tornado near Plains, Kansas, as you can see here, and as well as multiple tornadoes as it moved off toward the town of Ensign and eventually Dodge City. So very interesting setup, very similar to the Greensburg case. The overall sort of pattern, the upper air pattern, was not exactly the same. If we take a look at our 500 millibar map for May 24th, 2015, you can see that the trough, a little bit of a different positioning of the trough. The main sort of flow around the base of the trough situated well to the south, kind of situated near the core of the trough in this particular event. But still you had southwesterly or westerly flow across the Rockies, somewhat of a surface low out here across southeast Colorado. But overnight, the low-level jet started to ramp up. We'll go to 850 millibars here. and show you what happens with time. You can see throughout much of the day, 5, 10, 15 knots here across the risk area, so not much low-level wind to speak of throughout the day. But eventually, as we went into the early evening hours, the low-level jet really ramped up to about 30, 35 knots or so across the region, and we can see in the photographs for this particular event. These are some RAP photographs from May 24th, 2015. So we start early in the day, very similar situation. Lots of sort of capping issues there early in the day with a very minimal sort of severe weather photographs there to start the day. But notice what happens with that photograph with time. Very slowly starts to increase throughout the day, and that photograph in the low levels gets bigger and bigger and bigger. And eventually you see a very similar situation to the Greensburg case. Very strong looking low-level photograph there, almost 300 meters squared per second squared effective storm relative helicity. Lots of streamwise vorticity with this particular photograph as well. You can see, as we've talked about before, streamwise vorticity is that storm relative wind vector drawn to the photograph from the bunker's right storm motion, and our horizontal vorticity vector, which is perpendicular and to the left of the photograph. And when those two vectors are parallel, that's when you have streamwise vorticity. You can think of it as a NFL quarterback throwing a football with a perfect spiral. That is what the storms are ingesting, and when it's streamwise, it's already got that perfect spiral to it, or perfect rotation to it, to be tilted and stretched, and you can easily make supercells and tornadoes. Tornadogenesis is aided with increased streamwise vorticity. You can see a lot of that here in the low levels with this particular photograph. Also, a lot of streamwise vorticity here in the Dodge City photograph, or the Greensburg photograph, excuse me, from May 4th, 2007. You can see right here very ample streamwise vorticity with this particular event, with the Greensburg event in the low levels. So very similar situation where the low level jet ramped up after dark, and you had a similar situation where you had just a lone supercell fire out ahead of the main line and become a cyclic tornado producer. And although the upper air pattern not quite the same as the Greensburg case, this kind of increasing low-level jet situation definitely needs to be monitored when you have discrete supercells firing out in this region. When the low-level jet is set to ramp up significantly, you can get this kind of situation as we saw on May 24, 2015, and with the Greensburg case. So not something that is unusual at all with this particular Greensburg case. So storms first fired up here in kind of central to eastern Colorado. Of course, we talked about upslope flow, terrain influences, a little bit closer to the main wave, allowed storms to fire in Colorado first. You can see storms firing there in kind of central to eastern Colorado, near the foothills of the Rockies, and they moved off toward the east and eventually became severe as they went into better moisture. Then we had some development down here to the south along the dry line. As we talked about, it was a lot more conditional down to the south along the dry line. Let's pull up our Amarillo radar here. You can actually see the dry line here on radar. This was a little bit of perhaps a little dry line bulge there, a secondary sort of bulge. We saw that large dry line bulge up there into southwest Kansas. Little dry line bulge here across the northeastern panhandle. Again, we saw a little bit of convergence there in the low-level winds, or the surface winds there in the northeastern panhandle at about 22Z, right ahead of that shortwave, and we got some storms to fire just right about 22Z, 5 p.m. or so. You can see the first echoes here just across on the Texas side of the Texas-Oklahoma state line there in the northeastern panhandle. And these storms eventually quickly became severe given the amount of instability in the environment, and you can see they kind of continue along, and they become severe right as they cross into the Oklahoma side. Actually produced a pretty interesting tornado there early on. Of course, I'm sure most of you have seen this footage from Reed Timmer and Joel Taylor of the Ellis County, Oklahoma tornado. This was the first tornado, classic footage here of that drill bit tornado from that Ellis County supercell. That was this supercell right here. And notice it's putting off a lot of left splits at this time. The photographs, as we talked about, not quite, fully in a sort of, significant tornado parameter space, but just enough, given the strong instability and low-level instability, to initiate tornadic supercells here across the Oklahoma Panhandle. Lots of left splits, as you can see. That storm continues on toward the northeast. And eventually we get additional development out here toward the north near these other left splits. And you can see this storm firing up just here to the south, this little blip, just to the south of those that kind of area of left splits. That was our area of interest for our Greensburg supercell. You can see they kind of look like left splits moving off kind of toward the due north. But this new supercell on the southwestern flank quickly attained supercell characteristics, and that would eventually become the Greensburg supercell, producing several brief tornadoes near Sitka and Protection, Kansas. Here's a photo of one of those from the Lemon and Umscheid 2008 paper. You can see classic RFD cut there, wall cloud, brief tornado there. Produced, I believe, 4 brief tornadoes before the Greensburg tornado planted, just before 9 p.m. Central Daylight Time. You can see just an absolute monster in the dark there that started off as a much smaller tornado. This was the some initial photographs of the Greensburg tornado. Started off as a kind of slender tornado and eventually grew into the monster that we know it as, that was portrayed in quite a bit of video footage of the event. And there were several other tornadoes after that as well. As we talked about, this supercell produced 22 total tornadoes over a 6-hour period. This one was the Trousdale tornado, the cycle after the Greensburg tornado. Had some satellite tornadoes with it, as did the Greensburg vortex. We'll talk about the satellite tornadoes in a little bit. This was the Maxville large wedge tornado as well, and then the St. John, Kansas wedge tornado there. You can see the left side of that from this particular video still there. So very potent, high yield supercell as far as tornadoes go, and the environment definitely showed that it was a significant tornado event. So that's going to pretty much do it for the discussion of the meteorology behind the event. I do want to mention one more thing before we move on to talking about the storm behavior. As we saw on the soundings here, there was quite a bit of convective inhibition in the environment while the Greensburg supercell was ongoing, producing several significant tornadoes. And as we talked about before, convective inhibition can usually limit the overall amount of storms that fire, perhaps thwarting convective initiation altogether, or they can allow storms to become elevated rather than surface-based, which negates the tornado threat in most cases. But as we see in this case, the Greensburg supercell was able to produce multiple significant tornadoes, even though convective inhibition was increasing with time. And we also saw that with our May 24th, 2015 case, with our Plains, Kansas tornadic supercell, dealt with quite a bit of low-level stability, quite a bit of low-level convective inhibition in that environment as well. But in both cases, they were able to produce significant tornadoes regardless of that SIN. And so I want to bring to your attention this paper by Fisher and Davies, 2009. In this paper, they talk about significant nighttime plains tornadoes associated with stable low-level conditions. And in their conclusions, they discuss that the large Cape Shear parameter space in these cases tends to allow tornado production despite increasing low-level SIN. And low-level convective inhibition increasing after dark is a normal thing. As surface temperatures decrease, the low levels cool, and therefore you can see that convective inhibition building back in. But it's the overall large inhibition, large instability, and large low-level shear that plays a role. And I'm not going to go into the deep science and physics of this, but this paper by Rotuno and Klemp, 1982, talks about how low-level shear can actually induce a vertical pressure gradient or pressure perturbation that allows tornadic circulations and mesocyclonic circulations to kind of drill through that stable layer and produce tornadoes regardless. And that's why we often see in these kind of low shear, low CAPE, high shear cases, often in the southeast in the cool season, you might see just a couple hundred joules per kilogram of CAPE, but you see a very strong low-level shear, and you can still get a kind of big tornado event out of that. Well, that's because shear contributes to the buoyancy or the vertical motion in the environment. And again, I'm not going to go into the deep nitty-gritty physics of this, but when you have strong low-level shear, that adds to the vertical motion by inducing pressure gradients and pressure perturbations within that environment, and that can actually allow tornadoes to continue to happen despite increasing convective inhibition. And it does this by basically increasing updraft strength and aiding in the tilting and stretching of that horizontal vorticity or spin through that stable layer by those strong vertical pressure perturbations. And so that's how, oftentimes in these events, you can have strong low-level shear, but very strong low-level convective inhibition, yet still get tornadoes. And we saw this throughout the Greensburg tornado's life cycle. This was a photo from early on. I'll show this photo first from early on. This is from Tanamachi et al. 2012. This was a series of video stills here, and you can see the laminar layers here. the kind of pancake stack structure here in the early portion of the life cycle of the Greensburg supercell. That is, these pancake stacks, those striations, are signs of forced ascent through the stable layer. And we can also see that here with this particular picture from Lemon and Umscheid 2008. You can see as the Greensburg tornado was ongoing, that kind of pancake stack structure as well, continuing to indicate that forced ascent through that stable layer. All right, let's move on now and start talking about the overall behaviors of the storm and the tornadoes on the Greensburg day. We'll start off with the evolution of the storms leading up to the Greensburg tornado. And you can see here from this radar imagery that the overall sort of mode or progression of the storms, there was quite a preponderance of left splits. You can see, for example, this northern storm here starts off as one distinct core and then kind of splits into two different cores here over the next several scans. And this was the overall sort of progression of the storms for the first couple hours of the event. You can see we have kind of numerous left splits here. You can see the original sort of Ellis County supercell here splits off into two. And that continued until about 0030 to 01Z, until we started to get more of a right mover to happen. You can see here, particularly in this cell, as described right here on the Kansas-Oklahoma border, as described in Bluestein 2009, these were not traditional left splits. Instead of where you have one solid core and it actually divides into a left split and a right split, that was not exactly the case here. We'd actually have, you can tell by this storm right here on the Kansas-Oklahoma border, that it actually, the quote-unquote split occurs when a storm forms on the northern flank of the ongoing storm. You can see here that we get a storm to kind of just fire up there on the northern or northeastern flank of that ongoing storm right here. And that was kind of the mode of splitting, rather than full division of a single cell into two. And, splitting in general in this particular case was not a surprise. Generally, splitting supercells come when photographs are much straighter. Not much low-level shear. You tend to get a lot of splitting storms. But as we talked about in this particular event, that the low-level shear was increasing with time. You can see here at the 18Z Dodge City sounding, quite a straight-looking, straight-looking photograph, not much low-level shear at all. But then as we went towards 0Z, and we'll take the Lamont sounding here, we started to see an introduction of low-level shear into the environment. And this sort of unusual method of splitting probably was the result of an addition of that low-level shear, that increase in low-level shear with time in this environment. Where instead of having cells that split symmetrically into two, when you have a more straight photograph, we started to introduce some low-level shear into the environment, and that's how you get this sort of non-traditional splitting mechanism as modeled and discussed in Bluestein 2009. And then you'll notice with time, as we get toward the 1 to 2Z time frame, we kind of stop having splits altogether. As we talked about, this was the eventual Greensburg supercell, and you can see that we don't really have a ton of splitting going on with this particular storm. Maybe, as we talked about here, a little bit of just some additional sort of production of new cells on the northern flanks of these storms, kind of that non-traditional process. But by this time, the low-level shear was very strong, and the splitting had overall decreased quite considerably as we went into the kind of 1, 2, 3Z time frame as the Greensburg tornado was starting. So here again is our tornado track map from Lemon and Umscheid 2008, showing the 22 tornadoes that the Greensburg supercell produced. And you can see there's a pretty significant change in the overall characteristics of the tornado tracks between the first 4 that occurred near Sitka and Protection, and the next several that included these significant tornadoes near Greensburg, Trousdale, Hopewell, and Maxville. First of all, you can see that the first few tornadoes were very short-tracked, and then we transitioned to a much longer-track tornado mode. And you can also see that the overall motion of the tornadoes was much more to the left or toward the north than the next few. Generally, the significant tornadoes followed a more northeasterly path, aside from some more deviant motion characteristics. And we're going to talk about the deviant motion in just a second. So you can see that there was a distinct change between the first few and the next few, and this was a change in the overall mode of cyclic tornadogenesis. And cyclic tornadogenesis, just to define it, is when a supercell produces tornado after tornado after tornado in a cyclic fashion. You can actually have two different modes of cyclic tornadogenesis. You can have mode 1, which is your much shorter tracked tornadoes, and you can also have mode 2, which is your more longer tracked tornadoes. And so we started off with our mode 1 tornado production here with these first few tornadoes, much shorter tracked. And the difference between these two modes of cyclic tornadogenesis is that mode 1 has tornado motion that is to the left of the overall storm updraft motion. So if you imagine the overall supercell is moving more toward the northeast, but the tornado tracks more toward the north or to the left of the overall updraft motion. In mode 2, which is your more significant long-tracked cyclic tornadogenesis, your tornado path generally tends to follow the updraft motion. So again, you'd have your supercell moving toward the northeast, and your tornado would track kind of along that, more parallel to the overall updraft motion. So you can see we had a distinct change there, and this is outlined in Tanamachi et al. 2012. We had a distinct change between tornadoes 1 through 4 and 5 through 15, which was, it does include some of the satellite tornadoes we're going to talk about in a second, but the main significant tornadoes here occurred after these first 4. So these first 4 had Tanamachi et al. Tracked the updraft location with respect to tornado motion and did find that the tornado tracked to the left, perhaps because of occlusion processes, perhaps because of rear flanked downdraft, gust front surges, new updrafts forming along that rear flank gust front, and allowing the tornado motion to be more off toward the north. Whereas these more significant tornadoes, as we started the long track cyclic tornadogenesis mode, tracked more toward the northeast along with the parent supercell motion. Now, why this happened? Not entirely sure. As we talked about before, the overall low-level shear was increasing drastically throughout this time. Again, these happened between about 01 to 02Z, whereas these were all after about 2Z, these significant tornadoes. So there may have been a staunch increase in the low-level shear between 1 and 2Z and afterward that allowed this to happen. It's not entirely known why this transition occurred, but it is pretty clear that we had a transition between short-track cyclic tornadogenesis, mode 1 tornadogenesis, and your mode 2 tornadogenesis, which included the Greensburg and subsequent tornadoes. So now let's take a look at how the hook echo of the Greensburg supercell evolved leading up to and through tornadogenesis. So this is some data from the University of Massachusetts X-band polarimetric mobile radar that was used for the Tanamachi et al. 2012 paper. Thanks to John Wright IV on Twitter for this. His handle is on the screen there. But this is some really high-resolution data that can give us a really in-depth look at this storm that the WSR-88Ds just can't do. Because of the UMass X-Pole's radar's proximity to the storm and higher resolution, we can get a really good look at how the hook echo evolved here. So this is the data from the UMass X-Pole, and we're going to go on through a few, forward a few slides here. You can see early on in the life cycle, about 132Z or so, we start to get these little vortex signatures along the edge of the hook. You can see one right in there, maybe one starting right in there, right along kind of this hook echo. And so the fact that these are kind of isolated, small scale vortices, perhaps hint at the fact that these may have been more generated by just the stretching of vertical vorticity along some sort of boundary there, maybe the rear flank gust front somewhere in here, according to the Tanamachi et al. 2012 figure. You can see here at 136, I'm going to zoom in here just a little bit. This is at 136. You can see at the far western edge of the hook, you have our first tornado, that vortex signature we see right in here, just to the east of Ashland, and then we have the additional vortex signatures off toward the east. This was the tornado number 2 here, with the rear flank gust front kind of leading right up into it. So the fact that these are kind of more isolated signatures, more smaller scale vortices, tell me that these may have been more sort of the result of stretching of vertical vorticity along some sort of boundary, right along the gradient there of the hook. And we go on with time, we get, as we discussed before, we get a couple more tornadoes to develop near Sitka and Protection. So let's go back to the data here. We'll go forward in time, and you can see those vortices maintain themselves pretty nicely. I'm going to go forward here. So we go on with time, and we eventually see a pretty stark change in the hook. You can see that first tornado, westernmost tornado, very wrapped up there, very well-defined hook echo with that, kind of mini hook echo with that. These other tornadoes associated with maybe smaller scale hooks, as you can see in the Tanamachi et al. Data. You can see just these little hooks here associated with these other small tornadoes. Now, as we go through with time, you'll notice that this is about 140 Z. So the Greensburg tornado initiated at about 156 Z. You can see we go on with time. We have a broad area of inbound winds here, indicative of maybe the rear flank gust front fanning out there. Also, with that increase in inbounds, you can see the increase in outbounds as well. So strong convergence going on at the kind of tip of the elongated hook here. Very elongated hook right in here with multiple little areas of rotation associated with each of these vortices. But this tip of the hook, watch what happens over the next several scans. We go on with time, and you can see it really wraps up there on the western edge of the hook, and they change the view here. And then this was the genesis of the Greensburg tornado. Extremely wrapped up hook. These tornadoes, the earlier tornadoes, have dissipated, and this has taken over as the main hook, with the Greensburg tornado developing right at the apex of that hook, right about 2Z. And you can see that the tornado really gets strong very, very quickly and takes over with time. And those strong inbounds and outbounds associated with this tornado, the Greensburg tornado, indicate that, to me, that it may have been a little bit more with supercell dynamics at play here. Strengthening of the inflow, interface of that rear flank downdraft, and the inflow notch and that forward flank gust front, with some supercell physics going on. We won't get too deep into that, but this Greensburg tornado may have been the one that was really indicative of supercell dynamics at play, whereas the earlier ones, like I said, more isolated, more kind of weaker along sort of this gradient, along this hook echo boundary, elongated hook echo boundary here, may have been more so the stretching of vertical vorticity, or stretching of vorticity into the vertical. Another interesting feature of this hook echo, you can see here, this is at 222Z. Tornado is definitely ongoing now, very strong circulation there. You can also see these little vortices right in here, little couplet right in there, with perhaps some semblance of a little anticyclonic hook here. And if we zoom in to the figure on our Tanamachi et al. 2012 paper, you can actually see here is the ongoing Greensburg tornado, very strong vortex signature there. But you can also see these little vortex signatures just on the south or southeast side of the ongoing vortex. One of them, anticyclonic, and the other one is cyclonic. So there were some satellite tornadoes, as you can see on the track map as well, that from Lemon and Umscheid 2008, these little small tornadoes here on the exterior of the Greensburg tornado were satellite tornadoes, and you just saw a picture of it there from Umscheid 2010. You can see the Greensburg tornado ongoing with these two vortices right in here, just on the south side of the Greensburg tornado. That is an anticyclonic and cyclonic satellite vortex pair. Very interesting there. And these were the result, again, of the rear flank gust front and the stretching of vorticity into the vertical along that boundary, that rear flank gust front boundary. And that was what was able to create these satellite vortices in proximity to the ongoing large Greensburg tornado. Another interesting radar feature of the Greensburg tornado was that it produced what we call a weak echo hole, or WEH. And a weak echo hole, you can think of it basically as an eye, like the eye of a hurricane, so to speak. It's an area of weak reflectivity surrounded by stronger reflectivity that is coincident with the vortex. And you can often see that in supercells, usually with mobile radar data, almost exclusively with mobile radar data. Generally aloft, as we often see debris fill the low-level hook echo and increase the reflectivities there. But aloft, you can often see a weak echo hole. And so this is reflectivity of the Greensburg supercell at 237Z. So as the tornado was well into its life cycle, definitely into its mature phase. This is at the 3.1 degree elevation angle. And you can notice right here, this little area of weakened, decreased reflectivity surrounded by very strong reflectivity here. That is what we call a weak echo hole, or an eye, so to speak. This area right here is a bounded weak echo region, or BWER, BWER, and that's just an area that's indicative of the strong updraft within the storm, within the mesocyclone. Very strong upward motion within the mesocyclone, and therefore reflectivity decreases there, surrounded by stronger reflectivity. That's what we call a bounded weak echo region associated with the updraft of the storm. Now there's the smaller one here, that's the weak echo hole associated with the sort of eye coincident with the vortex. And if we go on through the next couple scans here, you can see that it maintains that weak echo hole through the next several scans right in there, even more defined there at 3.1 degrees. Let's go to 5.1 degrees. This is at 237Z. You can see that vortex hole right in there, bounded weak echo region right there. We'll go through the next few scans, and that vortex hole is very consistent here as we go up in height. This is at 6.4 degrees, even stronger looking vortex eye there. Next few scans stays intact as well, as does the bounded weak echo region associated with the mesocyclone. Here's even at 8 degrees. You can see that vortex hole, as Lemon and Umshai 2008 call it, otherwise known as that weak echo hole or eye associated with the Greensburg tornado. Now, this is not super notable because we've seen weak echo holes and eyes in tornadoes before. For example, the Doppler on wheels recorded a weak echo hole or eye within the May 3rd, 1999 Bridge Creek tornado right in there. You can see that little area of greens surrounded by browns and yellows there. That is the weak echo hole associated with the Bridge Creek tornado on May 3rd, 1999. However, as I said, this was documented by DOW, high resolution mobile radar. What makes the Greensburg radar presentation unique is that this was from the Dodge City WSR-88D radar. This was a much lower resolution radar compared to a mobile radar, and the fact that it was picking up this weak echo hole through multiple levels within the storm is really remarkable, and it really suggests that this Greensburg tornado was extremely, extremely strong, perhaps even stronger than the May 3rd, 1999 tornado, which from the KTLX or Oklahoma City radar did not pick up a weak echo hole. So very astounding, very remarkable that the WSR-88D radar from Dodge City was able to pick this up through multiple levels of the supercell, indicating a very, very strong vortex. And given that we have continuity of this weak echo hole with through multiple levels into the as you ascend in the storm, we call that a weak echo column, or WEC, because of that continuity. So very, very remarkable radar imagery there, showing a very strong mesocyclone, strong upward motion within that mesocyclone with the bounded weak echo region, and very strong looking tornado because of that weak echo hole, which is caused by the centrifuging of hydrometeors and other particles out of the tornado. The tornado basically whips those particles out away from the center, centrifuges them away from the center, and you get this lowered reflectivity right where the vortex is. So very interesting radar presentation with this Greensburg tornado. So now let's take a look at some radar here as the storm was progressing toward Greensburg. And you can see very strong couplet, starts to take a slight jog toward the north as it approaches Greensburg, and then it does something pretty unique. It actually does a loop on itself while the new cycle is beginning. And we can take a zoomed in look here. These are both radar images from US Tornadoes and their article on the Greensburg event. I'll put a link to that in the description below. Take a look at what happens here. We're zoomed in. This top left panel is reflectivity, top right is velocity. I believe this is rotation, normalized rotation, and this may be cloud tops here. So let's focus on these top two panels right here. So as we go on with time as the tornado is approaching Greensburg, very strong circulation hits the town of Greensburg and then does a pretty significant loop while the new circulation is forming just toward the west-northwest of Haviland. And the Greensburg tornado actually loops back around itself and tries to enter the northwest side of Greensburg once again. And so very interesting situation there. And that would be the pattern here for the remainder of the tornadoes. Very similar track with the Trousdale tornado. You can see it continues on, new circulation to the southeast of the ongoing tornado there, kind of does a little bit of an occlusion loop there, and then we have our new tornado that heads toward the St. John area. And we saw by the track map that these significant tornadoes here took a pretty interesting path. Particularly the Greensburg and the Trousdale tornadoes took a very similar looking path, starting off following the mean flow and then producing some deviant motion. So let's dive into the deviant motion here, and we'll talk about the Greensburg tornado here first. So As we talked about in the El Reno video, we can actually forecast any deviant motion a tornado might have based on the sounding technique given in Nixon and Allen 2021 and documented on Cameron Nixon's website here, his article on deviant tornado motion. So we can actually forecast the deviant tornado motion, what the motion of the tornado might take on when it starts to deviate from its following the storm's track. So what we do for that is we find the average wind in the lowest half kilometer of the atmosphere. So that'd be kind of somewhere right in here. Then we find our storm motion, which would be right there, given our bunker's right storm motion, 232 degrees at 27 knots. And we just find the exact middle point of that, and that would be right there. So our deviant tornado motion is pretty far off toward the northeast, pretty far off toward the left. And as you recall in the El Reno video, we said the farther that the tornado deviates from the sort of mean flow, the farther it has to come back to the left toward the end. And that's exactly what these Greensburg and Trousdale tornadoes did. So let's take a look at our path map. And we've talked about this before, that there are three different things that can modulate the deviant motion of a given tornado. The first can be strong downdrafts. So strong downdrafts from the rear flank downdraft surges, etc. That can push the tornado off in different directions. The second can be advection. So after the occlusion process begins, the low-level flow, usually out of the south or southeast, can actually push the tornado off toward the left, literally push it off toward the left of its current track. The third one is orbiting, and basically that can occur when the vortex kind of merry-go-rounds, if you will, around the mesocyclone. So it can kind of just orbit around the mesocyclone, and that generally can happen after the occlusion process toward the end of the tornado's life cycle. And we saw that here with the Greensburg tornado. We saw all three of these actually with these tornadoes. So let's go back to the track map here. So let's take the Greensburg tornado. Starts off through about here, following the storm motion, as does the Trousdale tornado, off toward the northeast. Then it takes a slight jog toward the left. At this point, the occlusion process begins, right about 238Z, and it might be a little difficult to ascertain here from this particular view. But if we kind of play this fast, you can almost see it start to take a little bit of a loop toward the left, or a little bit of a jog toward the left. So this is the tornado right here. Watch right about in here. It's going to take a little jog toward the north before it does that loop as it approaches Greensburg. So you can see it's traveling there, little bit, just a ever so slight northward turn of that tornado off toward the north. The Trousdale tornado actually had a little bit more noticeable loop. You can see there it's off toward the north and then really jogs off toward the north right about there. Again, the Trousdale tornado is that second tornado after the Greensburg one. So very interesting motion there. So they both start out kind of following the path of the storm. Then we take over with the occlusion process, and then the advection process takes over right about here. So literally the low-level flow out of the south or southeast is pushing the tornado off toward the left of its previous track. And then toward the end, you see it does that loop near Greensburg. Again, I'll show the radar imagery here as it approaches Greensburg. So it's being pushed by the low-level wind, then kind of does a loop around the mesocyclone. That is the orbiting process. You can see the velocity couplet does something like that. It is orbiting around the mesocyclone as it just passes through Greensburg and then tries to come back into Greensburg as the new Trousdale tornado is initiating. Another interesting thing to note here, watch this strong surge of rear flank downdraft as right after the tornado passes through Greensburg. You can watch these outbounds right in here, this little area of outbounds right in here. This is going to push out this way. This likely is a very strong RFD surge. Watch how it pushes really strong outbounds, and that may have had a little bit of an impact on pushing the Greensburg tornado back toward the south or southeast just a little bit, along with that orbiting process there. So very interesting, very strong surge of the rear flank downdraft there. You can see that those outbounds pushing out, and you can even see if we go back to our zoomed out radar, watch the hook echo of the storm really just kind of shoot out toward the right here. Just watch right about there, just a really strong surge. You can see that rear flank downdraft really just pushing out this way as it fills with hydrometeors, and that likely had a little bit of an influence on the tornado motion there during that occlusion process. So very interesting deviant motion. Again, we talked about the deviant tornado motion using the Hode graph was somewhere right in here, and that's exactly what both of these tornadoes did, as did the Hopewell tornado here. You can see they start off again following the storm motion off toward the northeast, then the occlusion process takes over, and then the low-level flow pushes them toward the north. Then they start to loop back around on themselves, and that is orbiting around the mesocyclone. So we have all three of those different types of different ways that you can get deviant motion within these tornadoes, and we were able to forecast the deviant motion after the advection process took over, somewhere out of generally toward the northeast, and that's exactly what these tornadoes did. And it may have pushed the Trousdale tornado off a little bit more to the right than what the Greensburg tornado initially started off with. You can see here the Greensburg tornado moving just a little bit more toward the northeast, a little bit more of a true easterly component to the flow, or to the motion of the Trousdale tornado initially. That could have been a result of that RFD push there that we just took a look at. And that brings us to the handoff process itself. So we talked about the radar, goes through Greensburg, does the little loop, and then very, very quickly, the new tornado, or new handoff, takes shape here just to the southeast of the dissipating original tornado. And that was the case for the Trousdale tornado, moving on, Trousdale and Maxwell tornadoes as well. So, as described in Lemon and Umscheid 2008, this was the result of what was perhaps the stretching of vorticity into the vertical along the rear flank gust front because of new updraft development over the gust front. So we can take a look here at our 6.4 degree scan here from Dodge City. This is at 237Z. We've already looked at this before to decipher the weak echo hole and that bounded weak echo region there just to the southeast of the ongoing tornado. Notice what happens here as we go on with time. That bounded weak echo region really gets strong here, just to the south of the tornado, which is somewhere kind of in this vicinity right there. So this is about the time that the handoff was occurring, and you can see that bounded weak echo region remains very, very strong. Now this is right over the rear flank gust front, and this was likely the mechanism by which the new handoffs occurred. You had your rear flank gust front somewhere kind of stretching along in here, and you had these updrafts. This was actually potentially a new updraft going up in the inflow region along that rear flank gust front, southeast of the tornado. This was able to, just like we talk about with landspout formation, whenever you have a boundary with strong spin or vorticity along it, and you have an updraft co-located with that vorticity right above it, it will be able to really stretch that vertical vorticity into the vertical, given very strong thermodynamics in the low to mid levels. And that's what we had here. You had this updraft going up right over the boundary, and given the strong shear that was in place, as we talked about before, that those intense pressure perturbations induced that vertical motion. We were able to really stretch that spin along that gust front, that vorticity along the gust front into the vertical. And that was the mechanism, likely aided in the initiation of the new tornado and completed the handoff process. Was also likely how we were able to get those satellite tornadoes as well, the stretching of that vorticity into the vertical along the gust front. Same process here. So as the Greensburg tornado dissipated, the original one did that loop. You had the new one right underneath that updraft. That updraft was able to stretch that spin right along the rear flank gust front there. That was also, kind of surging out. We talked about that rear flank gust front surge. That rear flank gust front surge catches up to that new vortex, and likely a continuation of that strong vorticity stretching into the vertical right there, eventually yielding a very large tornado, as we saw from this image. To close out this video, let's take a brief look at some of the subsequent tornadoes that occurred after the Greensburg tornado. So, as we talked about here, this is the Trousdale tornado, very strong vortex there. Very long track tornado, does the occlusion process, and there's your handoff to the Hopewell tornado, which also became a very strong and large tornado as well. One thing to note quickly is the similarity in the RFD surges here. As we just talked about, very strong RFD surge with the Greensburg tornado as the Trousdale tornado was initiating. Same thing here as we approach St. John. Take a look at the large kind of swing in the hook echo there. Very strong velocity surging out, very strong outbounds there, surging out and helping to aid likely in the strengthening of that tornado there. So Interesting evolution after the Greensburg tornado. And I want to turn your attention to this table from Lemon and Umshide 2008. Greensburg tornado statistics here on the left, Trousdale in the middle here. Greensburg, of course, rated EF5, Trousdale rated EF3. Thankfully, none of the tornadoes after Greensburg hit a ton of stuff, did not take any direct hits on any towns as the Greensburg tornado did, so they only received EF3 ratings. But notice here these width statistics. Maximum width for Greensburg about 3.1 kilometers, which is about 2 miles. Notice that the Trousdale tornado maximum width is about 4.1 kilometers, which is 2.5 miles. So the Trousdale tornado was an even larger tornado than the Greensburg tornado, and you can see here that the mean width of the Trousdale tornado was larger as well. So as much of a beast as the Greensburg tornado was, the Trousdale tornado was wider and perhaps even stronger than the Greensburg tornado. I want to turn your attention to this section of the Lemon and Umshide paper right here. This particular sentence on the Trousdale tornado right here. After 318, the tornado cyclone becomes extremely large with very high velocities. In fact, there appear to be even more successive range bins with very large velocities than at any point with the Greensburg tornado cyclone. So in basic terms, that just means there are more, stronger gate-to-gate couplet, a larger gate-to-gate couplet with the Trousdale tornado than there was at any point with the Greensburg tornado. So it is very conceivable that the Trousdale tornado was even stronger than the Greensburg tornado. As hard as that is to believe, as much of a beast as the Greensburg tornado was, you can see here from these statistics that the Trousdale tornado was actually wider and perhaps even larger than the Greensburg tornado. And just like the Greensburg tornado, the Trousdale tornado was associated with a vortex hole or weak echo hole as well. You can see right here, this is at about 307 UTC. There was the beginning of the vortex hole with the Trousdale tornado, as evidenced, as seen on the WSR 88D from Dodge City, and the radar was even farther away from the storm at this point. So the fact that the radar was still able to pick up a well-defined weak echo hole with the Trousdale tornado suggests that it was an extremely strong tornado. Again, perhaps maybe even slightly stronger than the Greensburg tornado itself. The Hopewell tornado was equally as intense, still large, not quite as large as the previous two tornadoes, but still large nonetheless. Maximum width of 2.2 kilometers there, so about a mile or so wide. Still a very large tornado. All of these were very long track tornadoes lasting about an hour each, and carving paths of 53 miles for the Greensburg, 53 kilometers for the Greensburg tornado, 43 for the Trousdale tornado, 33 for the Hopewell tornado. So these tornadoes after the Greensburg tornado were pretty impressive, and overall a very impressive supercell to continue to put down strong to violent tornadoes. Thankfully, these subsequent tornadoes didn't hit a ton as the Greensburg tornado did, or we'd be talking about likely multiple EF5 tornadoes from this particular supercell. So that's going to wrap things up here. I know this was another long video, as the El Reno one was, but this was a very, very interesting case, and wanted to convey a lot of things about it, as this was a really interesting storm from a meteorological perspective and a kind of behavioral perspective as well. So thanks for watching, and we'll see you in the next video.